Hello, I'm Dr. Daniel Wilson, and welcome to Lawrence Berkeley National Laboratory's instructional video course on laboratory testing of cookstoves. Today's lesson will be on the design of hoods for your laboratory testing system. In a laboratory cookstove testing system, a hood enables the total capture method. The total capture method captures all emissions from a cookstove, then mixes those emissions with ambient air before sampling. The total capture method is in contrast to partial capture methods. Partial capture methods do not capture the entire emission plume and instead use a mass balance of an elemental tracer, typically carbon, to back calculate total emissions. However, the total capture method is highly preferred as the most reliable and repeatable way to perform laboratory cookstove testing. The primary advantages of the total capture method are that 1. It ensures an average of total emissions is sampled at the sampling port, and 2. All emissions are cleared of the testing environment. However, this comes at the expense of a relatively large testing setup that is not very mobile, and a significant amount of construction and commissioning effort are required before testing can begin. A high-quality hood is the foundation of a laboratory cookstove testing system. If your hood is designed well, it will capture all the emissions emitted by the cookstove being tested both during an active test and while extinguishing fuel. It will not draft the cookstove or induce any significant air velocity near or inside the cookstove being tested. A good hood will minimize in-hood residence time while preventing eddies. The hood will provide the tester plenty of room to work freely and safely. And finally, the hood will transition to a high-quality ducting system. To discuss these topics in more depth, let's use this graphical representation of a cookstove testing hood. A cookstove testing hood is made up of 5 components, the first being the base. The base of the hood is optional and can be replaced with a platform or testing table. Optionally, the base of the hood can be sealed. Second is the opening or door of the hood. The door is to remain open if the base of the hood is sealed. If the base of the hood is open and the testing platform leaves sufficient open area for air to flow freely into the hood, the doors can be closed. Finally, your hood should have walls, an angled ceiling, and a transition to the duct. One of the most important considerations when designing your system is to reduce the face velocity of air entering the testing hood. The face velocity of air entering the hood is controlled by the volumetric flow rate through the exhaust blowers and the open area where air passes from the room into the hood. The open area should be calculated when it's at a minimum, for example when hood doors or sashes are closed, or when large testing platforms restrict the open area into the hood. To calculate the minimum open area for your hood, use the equation open area equals volumetric flow rate over maximum face velocity. The maximum face velocity recommended by the International Standards Organization is 0.25 meters per second. Also, you need to assume a volumetric flow rate. Many blowers are designed for an installed volumetric flow rate of about 0.1 cubic meters per second. You should use your real-world volumetric flow rate, but assuming 0.1 cubic meters per second, the minimum open area of the hood should be about 0.4 square meters. Although this analysis suggests that we only need an open area of 0.4 square meters, ergonomics may demand more open space. The International Standards Organization recommends an open area of 1.2 meters by 0.6 meters to allow for sufficient airflow and sufficient room to work. This open area is almost twice our calculated minimum opening. We recommend that your open area be of sufficient size so that you can easily reach your testing platform or auxiliary scale without any awkward stretching or reaching around any corners. We also recommend that your door be sized such that the top of your door be higher than the top of the tallest cookstove you plan to test inside your hood. This will help significantly when moving the cookstove in and out of the testing hood. We also recommend that exhaust leave the cookstove into the hood's widest section. We do not want the suction from the duct to pull air through the cookstove and draft it. You can see in this extreme example, a very tall cookstove may approach the narrow section at the top of the hood, leading to draft. We want to avoid this situation. We recommend that the sealing of the hood be angled at all locations before the duct. This will help prevent eddies. Eddies are local areas of swirl in the hood where emissions can reside for a long period of time. We want all emissions to have roughly the same residence time in the system before the sampling port, and therefore we want to reduce eddies. You can do this by ensuring that the sealing of your hood is angled at 20 or more degrees at all locations leading to the duct. Finally, you need to transition your rectangular cross-section hood into a circular cross-section duct. This can be difficult to fabricate by hand, but there are commercially available products designed specifically to transition from square to round cross-section ducting. By reducing sharp corners, you can reduce eddies and particle loss. The transition terminates at a circular duct, which the ISO recommends be between 10 and 30 centimeters in diameter. Here is a summary of all the hood design principles we have discussed in this lesson. In summary, ensure your hood captures all emissions from your cook stove. Additionally, design your hood with enough open area to limit face velocity below 0.25 meters per second. Your hood and door should be large enough to work comfortably in before, during, and after your test. Your hood should evacuate emissions quickly and without forming eddies. And finally, transition your hood into a round cross-section duct. Thank you. I'm Dr. Daniel Wilson from Lawrence Berkeley National Lab. Please join us for our next instructional video on laboratory testing of cook stoves.